Clampers. What is a clamper? It is a circuit which it's an electronic circuit which adds a DC to the given input signal. Okay, or which shifts the DC level of an input signal. Which means, see, suppose I have a sine wave like this, some 5 sine omega t. What is the DC level of this particular signal? 0. Okay, and it has a peak amplitude of 5 volts. We can take positive peak 5 volts and negative peak value is minus 5 volts. When this is passed through a clamper circuit, the output is also a sine wave. It does not disturb the shape of the signal, but it shifts the DC level of the given input. Means the output of this particular signal may be something like this. Means, see here it is inserting a DC or adding a DC of 5 volts to the given input, which is just nothing but the positive peak. Positive peak is 5 volts, that much DC is inserted in the given input without changing the shape of the input. And the output equation is given by 5 plus 5 sine omega t. This is one possible output. And another possible output is it inserts a DC of minus 5 volts, which is nothing but the negative peak of the input signal. Here it is minus 5 and it is minus 10. Now how can we write that equation? Minus 5 plus 5 sine omega t. Means the clamper circuit is adding a positive DC whose value is equal to positive peak of the input signal. This is one possible output. And the clamper circuit may add a negative DC to the given input, which is equal to the negative peak of the input signal. That's without altering the shape of the input. Okay. Also, the added DC need not be exactly equal to plus 5 or minus 5. Okay. There are another possible outputs like this. Okay. This is the issue. Our output may be something like this. It is minus 7 volts. V output is minus 7 plus 5 sine omega t. We can achieve even this kind of output also. Or the output may be something like this. Means 2 volts DC is added. So V output is equal to 2 plus 5 sine omega t. Means 2 plus 5, it is 7 volts and 2 minus 5, it is minus 3 volts. All such outputs are possible. Okay. Of course, how the clamper circuit appears, which gives this kind of output and all, we need to discuss. Just what is meant by clamper. Clamper is an electronic circuit which adds some DC to the given input or which shifts the DC level of the input. Okay. In this, you can see in the first case, the negative peaks are appearing with respect to ground, shifted to 0 level. Or in the second example, the positive peaks are shifted to the 0 level. All such things. Or here, all positive peaks are shifted to minus 2 volts, and here the negative peaks are shifted to minus 3 or positive peaks are shifted to plus 7 volts, like that. All such combinations are possible. And one more thing, the input need not be exactly 5 plus 5 sine omega t. It can be some 2 plus 5 sine omega t, just as an example I am writing, or 12 plus. Okay, or it may be minus 1 plus 5 sine omega t. All such things are possible. Input also need not be pure AC. It may have some DC level of 12 or it may have a DC level of minus 1 volt. All such things are possible. Then we can achieve all these combinations of outputs. It has its own limitations, of course. We will see that. So ultimately what we are doing, we are shifting the DC level of the given input. That's it. A circuit which performs this kind of operation is a clamper. Then see this. A clamper is an electronic circuit that changes the DC level of the signal to a desired level without changing the shape of the applied signal. First part, as I said. In other words, a clamper circuit moves the whole signal up or down to set either positive peaks or negative peaks at the desired level. Yes, you are shifting up or down. This is the input signal. You are shifting it up or down. Alright, here it is down, again here it is up. You are shifting it up or down to set the positive peaks or negative peaks at a desired level. In this example, we are setting all positive peaks at 10 volts or negative peaks at 0 volts, like that. Okay, here all positive peaks are set to 0 level and negative peaks are set to minus 10 volts. So that's the meaning of it. The DC component is simply added to the input or subtracted from the input signal. See, uh, actually we are adding DC. If you add positive DC, that is like regular addition only. And if you add a negative DC, that is like subtraction. Adding a negative number to a positive number is nothing but subtraction. That's it. So we are adding a positive or negative DC. A clamper circuit adds a positive DC component to the input signal to push it to the positive side. Absolutely. When you add a positive DC, signal is pushed upwards, vertically upwards. And similarly, if you add, and a clamper circuit adds the negative DC component to the input signal to push it to the negative side. Yes, when a negative DC is added, then it is pushed downwards or negative side of the y-axis. If the circuit pushes the signal upwards, then the circuit is said to be positive clamper. Yes, if the added DC is positive, signal will be pushed upwards and we call that as positive clamper. Okay, and how does the circuit appear means, this is how the circuit appears. We have to see the working of this circuit. And how to remember the circuit in a very simple manner. If the diode is upwards, signal will be pushed upwards. Very, very simple thing. And similarly, right, if you take a negative clamper and if you take this particular circuit, what it contains is simply a capacitor, a diode, and a load resistor RL, which is optional. Okay. Also, it may contain some DC source in series with the diode. That is also possible. Without any DC source, if you see the circuit, simply it shifts the DC level or it adds a DC which is equal to the peak amplitude of the input. Okay, diode is upward, it is adding a positive DC to the given input, so that signal is pushed upwards by an amount equal to peak amplitude of the input. Or all the negative peaks will meet the 0 level. Okay, when a signal is pushed upwards, the negative peak of the signal meets the 0 level. That's the thing here. Similarly, if the circuit pushes the signal downwards, yes, here see the direction of the diode. It is directed downwards. It will. So if you take its working after that, the end, what you understand is signal will be pushed down by an amount equal to the negative peak of the input. In this example, the negative peak is minus Vm. That is the DC added to the input, so that all positive peaks will touch the ground or they meet the 0 level. That's the idea here. Next, what does a clamper contain? A clamper has a capacitor, diode, and optionally a resistive element, which is known as the load, of course, and also employ an independent DC power supply to introduce an additional shift. Okay, so what is the meaning of it? See, without the DC power supply, the shift is equal to the peak amplitude of the input. Okay, without DC source. With DC source means in this example, suppose I add 2 volts DC, then this signal will be further shifting upwards by an amount equal to 2 volts. Okay, so its output is like, it is also a sine wave, no doubt about it. And what about the added DC. Without this 2 volts, the added DC is equal to Vm, and with 2 volts, the added DC is equal to Vm plus 2. Okay, and output here maximum is 2Vm plus 2. Output minimum is equal to minus Vm plus 2. Sorry, I can say not minus Vm plus 2. It is just 2. The difference is Vm, no? Yes. Like this. And of course, the added DC need not be positive. It can be negative also. If it is negative, then signal will be pushing down further by an amount equal to the negative value. DC source. You are connecting in series with the diode. Okay, this kind of circuit is also possible. Minus 1 I added. So instead of plus 2, I should write here minus 1, and here also minus 1. Okay. The same thing is possible with a negative clamper as well. We can have a clamper circuit, negative clamper with a positive reference voltage, or we have a negative clamper with negative reference voltage. 2 or 1, whatever it is. We can just check all the combinations and what level we can take these reference voltages. There is a limitation, of course. You cannot, we don't have the reference voltages according to our wish. There is a limitation. We will discuss all those things. Okay, that's a bit. Next. The magnitude of R and C are chosen such that the time constant RC is large enough to ensure that the voltage across the capacitor does not discharge significantly during the interval the diode is non-conducting. Okay, what is the meaning of this statement? I will explain it along with the operation, of course. And the capacitor forms a time constant with the resistor load, which determines the range of frequencies over which the clamper will be effective. Okay, but that always, right? Once you have a circuit, means it has its own limitations as far as its working is concerned. You cannot use any signal of any frequency of your choice. There are some limitations in the frequency, and that limitation is decided by the capacitor and the resistor connected in parallel with the diode. Okay, and one more thing, the input need not be a sine wave. Just for our understanding purpose, I wrote sine wave here. The input can be a triangular wave or square wave. Okay, some other periodic waveform. Anything is possible. Okay. Next, types of clampers. Clamper circuits are of 3 types. Positive unbiased clamper means the very basic positive clamper circuit. This is positive unbiased clamper, and this is positive biased clamper. In biasing in the sense connecting a DC source in series with the diode. So you may connect a positive source or a negative source. This is called biased clamper, biased positive clamper. These two are biased positive clampers. This is positive unbiased clamper. Similarly, this is negative unbiased clamper, and these two are negative biased clampers. Okay, these are the different categories: positive clamper, positive unbiased clamper, negative unbiased clamper, and finally biased clampers. Okay, these are the categories. Now coming to the applications. Okay, positive clamper. Anyway, I have discussed them. Just you can see the output equations. In the negative quarter cycle of the input AC signal, the diode is forward biased and conducts, charging the capacitor to a peak negative value of V. We will see that the statements and all. I will clearly explain all those things. Okay, during the negative quarter cycle of the input, the diode conducts and the capacitor will charge up to minus Vm. So capacitor will charge like this, minus Vm in the sense. If the diode conducts, the current will flow like this, means the polarities of the voltage across the capacitor should be like this. That's why, right? Capacitor will charge up to negative peak. Once it is charged, then in this, if you take V input is equal to voltage across the capacitor plus V output, and V capacitor, it is equal to minus Vm. We can take. I'm just taking V capacitor with polarities like this, V output polarities like this. So V capacitor is equal to minus Vm. So what is V output? It is V in minus V capacitor. V input is equal to Vm sine omega t, and V capacitor is equal to minus Vm. Ultimately, what you can see, Vm plus Vm sine omega t. What is V output? V input plus V input peak. What is V input peak? The capacitor has charged up to the negative peak, but the final equation is like Vm. V input is Vm sine omega t, and V input peak. What is V input peak? Vm. This is what. Okay, that's the meaning of this statement. Okay, during the positive cycles, the diode is reverse biased and thus does not conduct. The output is therefore equal to the voltage source across the capacitor plus input voltage. This is the idea. Okay, this is also called as, right, Willard circuit, the positive unbiased clamper. Of course, clamper circuit is known as Willard circuit, right? In this positive clamper, this one. And negative clamper, if you take a negative unbiased clamper, is the opposite of equivalent positive clamper. In the positive quarter cycle of the input signal, the diode is forward biased. Here, the positive quarter cycle, only the diode will conduct. And the capacitor will charge up to the positive peak. Means, if the diode conducts, the current will flow like this, plus minus, and the capacitor will charge up to Vm. So that V capacitor is equal to Vm. As usual, if you take the loop equation, V input is equal to V capacitor plus V output. And what about V output? It is V input minus V capacitor. It is equal to Vm sine omega t minus Vm. We can observe. So minus Vm. So output waveform will be like this. Or here it is written V in minus V input peak. In positive clamper, output is V in plus V input peak. Negative clamper, it is V in minus V in peak. So V input is Vm sine omega t. And what is the peak amplitude of the input? Okay, it is Vm. Okay, this is how we can write it. Or simply speaking, the best way to remember the things is, in positive clamper, V output is equal to V input minus negative peak of the input. What is the negative peak? Minus Vm. Whatever it may be. Okay, so input minus negative peak of the input. That is the apt way to write it, strictly speaking. The books and all, they may write like this, but the best way to write is this. And here, in this case, V output is equal to V input minus positive peak. In the negative clamper, V input minus V, right? It's a positive clamper or negative clamper. V output is equal to V input minus V capacitor. V capacitor, all right? Here in negative clamper, the capacitor will charge up to the positive peak, and in positive clamper, the capacitor will charge up to the negative peak. We'll see these things. With a positive biased clamper, means some DC source is connected in series with the diode. Then what happens is the output will shift up by an amount equal to V reference. Okay, what is this waveform and all? We will discuss. Don't worry. It is shifting up by an amount equal to V bias. And the V bias need not be positive, it can be negative also. Okay, so that time what happens? Okay, don't worry about this, I will explain it. Instead of V in plus V input peak, we need to add that bias voltage, V bias, which may be positive or negative. That's it. Earlier I wrote V input plus V input peak. Instead of that, we need to add V bias also. Again, the negative biased clamper. Right here also, a DC source is connected in series with the diode, and the signal is pushed down by an amount equal to, it is further rising by an amount equal to V bias. This difference is V bias. Actually, what happened is it is a negative source. That's why it is further going down. And it need not be negative. It can be a positive DC source also. If that is the case, signal will be moving upwards. We'll see all those circuits with proper explanation. Applications of these clampers. They are used in direct current restorers. Right? So these clampers are also known as DC inserters or DC restorers. Other name for clampers. Even I can take here, also known as DC inserters or DC restorers. The other name for clampers or level shifters. They are shifting the DC level. How it is so? We need to check it. Of course, they are used to meant for removing the distortions. We'll see all those things. Just applications I'm mentioning. We need to discuss these things. Voltage multipliers. What is meant by voltage multiplier? That is the very next topic after this voltage clampers. Right. Once the clamper is done, voltage doublers, voltage tripler, voltage quadrupler, voltage multiplier. All those things we will be studying. And protection of amplifiers and all upcoming topics we'll see. Baseline stabilizers. We'll see. These are some of the applications of the clampers. Okay. Let us start with the negative unbiased clamper. I'm not starting with positive biased clamper because it is negative unbiased clamper is easy to understand. Later we can extend it to positive clamper, biased clampers, etc. Okay. As I said, the output equation is given by V input minus V input peak, or apt meaning is V in minus V capacitor, or it is V in minus V capacitor is equal to positive peak. Okay, what is the working of this particular circuit? See this. Right. Anyway, just took the waveform, nothing to worry. I will rewrite these things again. So, what I'm doing is I'm just taking a sine wave input. Okay. Negative clamper. I'm writing the waveforms here. Just for our example, better understanding, I'm taking it like V input is equal to 5 sine omega. With some numericals, it is very easy to understand. Nothing else. Here, 0, t by 4, t by 2, 3t by 4, t, 5t by 4, 3t by 2. Like this. So, our clamper circuit is basic clamper circuit. I'm taking this way. Capacitor, I can say V capacitor with polarities plus minus. VD, voltage across diode, or V output, both are one and the same. I'm starting with the very basic clamper without load. Later we will see the what is the purpose of the resistor R. Okay, as of now I'm starting with this clamper circuit this way. And what can we write here? Here we can write V input is equal to V voltage across the capacitor plus voltage across the diode. Okay. Now at t is equal to 0, what is happening? Input is 0, diode does not conduct, and assuming 0 initial conditions. Okay. Assume 0 initial conditions. So at t is equal to 0, V input is 0. So implies diode does not conduct, and capacitor acts as short circuit. Voltage across the capacitor is 0, and hence it acts as short circuit. Okay, keep it aside. Now, for t greater than 0, the diode starts conducting, assuming ideal. If the diode is ideal, what happens? Input is a positive going signal, immediately the diode starts conducting. So, for t greater than 0, or I can take 0 to t by 4 I am taking. 0 less than t by 4. Means during the first quarter cycle, positive quarter cycle. The input is a positive going signal and the diode conducts. See friends, it is not negative half cycle, it is it is not positive half cycle, it is positive quarter cycle only. Only positive quarter cycle. The diode is conducting. Once the diode conducts, it almost acts as short circuit. And the equivalent circuit, if you take, I am just replacing the diode with its equivalent forward resistance RF. And the current flows like this. And the capacitor will charge with polarities plus minus. V output or VD, VD or V output. So here what I can take is the capacitor starts charging towards input with a time constant RF into C. Okay, and VD is almost negligible. Or in the equation, V input is equal to V capacitor plus VD, and neglecting VD, V capacitor is approximately equal to V input. Ideal diode, if I take so, voltage across the diode is almost negligible compared to the capacitor. Means the capacitor rapidly charges towards input with a time constant RF into C. I am not saying abrupt. Input is also not varying abruptly. Input is varying sinusoidally. Okay. So implies the capacitor rapidly charges towards input with time constant tau c, charging time constant is equal to RC. Okay, it is fine. Means if you take the waveforms, V output is almost 0 and the capacitor is rapidly charging towards input. Input has a peak amplitude of 5 volts. But strictly speaking, first the input rises, next the capacitor tries to capture the input. There is small delay. Anyway, there is a time constant possible practically speaking. Okay, the capacitor is rapidly charging and it is falling. Almost it is equal to the input voltage, we can say. Okay, now at t is equal to t by 4, at t is equal to t by 4 minus, I'm just writing, right? Or at t is equal to t by 4, V input is reaching its peak amplitude of 5 volts. Okay, and due to small delay, because the input is rising, input is on its own, next the capacitor is trying to capture the input. It is like teacher is delivering some lecture and the student is following what the teacher is explaining. There is a small delay. Okay, there are some exceptional cases, extraordinary students, they may go beyond what teacher is teaching. That's a different story. General case I'm speaking. A teacher is delivering lecture and student is following. There is small delay, right? Always it is possible. Due to small delay, V capacitor is not exactly equal to 5. It is some 4.9 or 4.95 volt, like that. Slightly less than input voltage. Okay. Then for t greater than t by 4, after t by 4, what happens is the input tries to fall below its peak amplitude. V input is just falling below 5 volt. By that time, the capacitor reaches 5 volt. I hope you understand. Right? Because it is running behind the capacitor voltage, capacitor is running behind the input rises. By the time it is about to reach, then input tries to fall. By the time the capacitor reaches the peak amplitude, that's the meaning of it. Then what about your VD? VD is equal to V in minus V capacitor. Okay, so from this what we can do is, right, which implies VD is equal to V input minus V capacitor. What is V input? It is 4.9 and V capacitor is 5. It is equal to minus 0.1 volt. It is looking negative. Diode voltage is negative. Diode is experiencing some negative voltage. When the diode experiences negative voltage, immediately the diode becomes off. Okay, so implies the diode becomes off. Once the diode is off, what is the equivalent circuit? And once the diode is off, this is the equivalent circuit. If so, is there any path for the capacitor to charge or discharge? No. The capacitor has no path. Now, the capacitor can neither charge nor discharge. This is the equivalent circuit. Now, the capacitor can neither charge nor discharge, as it has no path. And simply it acts as a DC source or battery. As it is unable to charge or discharge, whatever the voltage it has acquired, it holds that voltage forever. That's it. And what voltage the capacitor has acquired? Plus minus Vm, or I can say plus minus 5 volt. Okay, look at the polarities. Because once the current is flowing like this, the capacitor will charge with polarities plus and minus this way. And to what level the capacitor has charged? Up to Vm, the positive peak of the input signal. And it can neither charge nor discharge because the diode is off. It has no path. There is no scope for the capacitor to charge towards input nor the discharge the voltage it has acquired. This is the idea. Then what about the output, right? And it maintains, right? The capacitor can neither charge nor discharge and acts as a DC source with by maintaining the voltage of 5 volts across it. Acts like a DC source or battery of value equal to peak amplitude of input. What is the peak amplitude? In this example, 5 volt. The peak amplitude of the input is 5 volt. Okay. Now, right, so now what we can write for VD? VD or V output is equal to V input minus V capacitor. What is V input? It is 5 sine omega t minus V capacitor is 5. Capacitor voltage is fixed at 5. Why the capacitor is unable to charge further? We'll see that again. Now, as of now, this is a circuit we are observing. From this circuit, what we can understand is the capacitor can charge neither charge nor discharge. It cannot follow the shape of the input. There won't be, there is no possibility of charging towards the input voltage or following the shape of the input. Okay. Now, at t is equal to t by 2, what is our VD? T by 2, I'm speaking. After one more quarter cycle, input is falling by 5 volt, but the capacitor voltage is not changing. Then what happens to the output? Whatever the change you have in input, that has to appear across the output. You see, our KVL, V input is equal to V capacitor plus VD, and capacitor voltage is fixed at 5. Whatever the variations you have across input, all those variations can be seen across the diode only, or the diode voltage. How the input is following the same shape you can see across the diode. So from T by 4 to T by 2, input is falling by 5 volt and V output also falls by 5 volt. Okay. Or at T is equal to T by 2, input is 0, V capacitor is 5. Overall, VD is minus 5. It is negative. Yes. Next, at T is equal to 3T by 4, VD is equal to, at 3T by 4, input is further falling by another 5 volts. It is constant. Then all those variations can be seen across the. So input is further falling by another 5. It also falls by another 5. So output reaches minus 10. At 3T by 4, input is minus 5. V capacitor is 5. Ultimately, our output is minus 10. Okay. Next, at t is equal to capital T, at the end of one period, again V input is 0, V capacitor is still 5, so our output is 5. Input here is rising by 5, it is constant and it will rise by 5. It reaches minus 1. Further, at 5T by 4, means here input is rising by another 5, V capacitor is constant, this will also rise by 5 volt. So to what level it will rise? It will rise up to 0 volts. At T is equal to 5T by 4, VD is equal to, input is plus 5 and V capacitor is 5, it is 0 volts. Okay, output is reaching a maximum of 0. Next, further what happens? Input is not further rising. If it rises, then there is a scope for VD to positive. Then there is a scope for diode to conduct. But it is not happening. So input is falling. So whatever is taking place here, the same thing is taking place here. So input is further falling by 5, so it is constant. And why, right, from this point to this point, if you see, this point if you see, right, the output is completely negative, or VD is negative. VD is negative means diode cannot conduct. That's the reason why the capacitor is unable to charge or discharge further. It is acting like a DC source or a battery whose value is equal to the peak amplitude of the input. Further, input falls by 5 and next it also falls by 5. Same story repeats. Whatever has happened from here to here, the same story repeats for next cycle. So again further it falls up to minus 10 like this. Always our VD is negative, or at T is equal to 3T by 4, VD is equal to, input is 3T by 4, sorry 6T by 4, or 3T by 2 I can say. 3T by 2. What is input? 0. So V capacitor is 5 and V output is minus 1. So if you observe this, V output is or VD is always negative only. At a max it can reach 0. If it is positive, then only there is a scope for a diode to conduct. As long as the diode is not conducting, the capacitor holds the voltage it has acquired. Then the capacitor has charged up to the peak amplitude of the input. Now you understand better the statements I have mentioned earlier, all these statements. Negative clamper. Negative unbiased clamper is opposite of the equivalent positive clamper. In the positive quarter cycle of the input AC signal, the diode is forward biased and conducts, charging the capacitor to the peak positive value of input. And during the negative cycle, the diode is reverse biased and diode does not conduct. The output is therefore equal to the voltage stored across the capacitor plus input voltage. Okay, voltage stored across the sorry with the negative sign we should take, right? I will change this statement. So negative clamper now V input minus voltage stored across the capacitor, right? As I write, input minus negative P. Okay, so equal to the input voltage minus voltage stored across the capacitor, not plus. The input voltage minus the voltage stored across the capacitor. That is the correct statement. There is a mistake in the statement. Please check it. Okay. Now the reason why the waveform is like this, you can see this. Okay. So still there are so many things to discuss here. I wrote the waveform like this for negative clamper. This is the apt one. Everything is fine. And why it is so? It is from 0 to T by 4. First quarter cycle, the diode does not conduct. Sorry, diode conducts and almost acts as a short circuit. Hence, you are getting the output like this. Okay. Next, further, if you take this as the transient portion, the moment you give the input, immediately you won't get the output. Definitely, every system has its own transient. And removing this transient, looking at the steady state output, in steady state, I can say neglecting the transient response, I can take it as transient. Okay. Neglecting this transient in steady state, the output is given by neglecting the transient response. We can write the output equation to be like this. Here, all positive peaks are shifted to the ground level. Negative peaks are shifted to minus 10 volts. That's it. This is how we can take the steady state output of a negative clamper. Why the name negative clamper means, as the inserted DC is negative, it is called negative clamper, or it is also known as positive peak clamper. Positive peaks are shifted to the ground level and hence it is known as positive peak clamper. Positive peaks are clamped to the ground level. Right? The circuit, it is known as the circuit. Negative clamper is also known as positive peak clamper. Right? It's hence the name. As the inserted DC is negative, it is known as negative peak clamper. Sorry, positive peak clamper or negative clamper. Why the mistakes? Okay, like this. And further, different cases I'm taking. Right, we'll see what for the resistor is kept and what happens if a DC source is connected in series with the diode and all those things we need to see. First, according to the definition, few more things I would like to discuss here. Suppose in the same negative clamper, my input is something like 3 plus 5 sine omega t. Then what is the output? As usual, I am taking V capacitor with polarities plus minus. V input is equal to V capacitor plus VDR, V output. What is the output of this particular circuit? Okay, see. I'm just looking at the first quarter cycle only, 0 to T by 4. Okay, and here it will be T by 2. Nothing to worry about it. Here it is 3 T by 4. Again, it is T. V output. As usual, with 0 initial conditions across the capacitor, what happens? 0 to T by 4, the diode is on. Input is positive. Okay. And 0 less than T by 4, diode is on. Once the diode is on, almost it acts as a short circuit, or the capacitor will rapidly charge towards input with a time constant RF into C. We can take. So here as usual, right, V input is equal to V capacitor plus VD. We know that. So V input is equal to V capacitor plus VD, and VD is almost negligible, implies V capacitor is approximately equal to V. Almost all the input can be seen across the capacitor. Okay, so means the capacitor rapidly charges towards input with a time constant RF into C. Same story only. Okay, it is starting. The only concern here is, right, capacitor voltage cannot rise abruptly. There is small delay, right? But what is the peak amplitude of the input here? 3 plus 5, it is 8 volts. Means the capacitor will rapidly charge up to 8 volts. Okay, up to the peak amplitude. not 5 volts. What is the peak amplitude of the input? Capacitor will always charge up to the peak amplitude of the input. Peak amplitude of input. Okay. Now at t is equal to t by 4, what happens? Input is equal to 8 volts, and due to small delay, V capacitor is slightly less than 8, maybe 7.9 volts, like this. So next, for t greater than t by 4, just the input is falling below its peak amplitude, that is V input is equal to some 7.9 volt, and by that time the capacitor reaches the peak amplitude. If that is the case, the Vd is equal to V in minus V capacitor. It is equal to 7.9 minus 8, which is equal to minus 0.1 volt, negative. When Vd is negative, immediately the diode becomes off. Once the diode is off, what happens? There is no path for the capacitor neither to charge nor discharge. Okay, up to this point, almost Vd is 0 and V input is equal to V capacitor. We can see. Then, so once the diode is off, the equivalent circuit is something like this. And what about the capacitor voltage? Capacitor has charged up to 8 volts, peak amplitude of the input. Later, the capacitor can neither charge nor discharge. So, what is our output? Vd. If you take, once the diode is off, then Vd is equal to V input minus V capacitor. V input is 3 plus 5 sine omega t minus V capacitor is equal to 8 volts. Ultimately, what is the equation? Minus 5 plus 5 sine omega t. That's it. See the interesting point here. The output equation is not changing. Or if you see the waveforms here onwards, right, the capacitor is neither charging nor discharging as the diode is off. It holds the voltage of 8 volts forever. It is neither charging nor discharging due to this equivalent circuit. Okay, the capacitor can neither charge nor discharge. Then whatever the variations you have in input, all those variations can be seen at the output. Because Vin is equal to V capacitor plus Vd, it is constant at 8 volts. Then whatever the variations you have in input, all those can be seen across the diode. Means input is falling by 5, the same 5 volts fall you can see at the output. It falls up to minus 5. Further, input is falling by another 5 and capacitor is voltage is constant, so output also falls by another 5 minus 10. Next, input rises by 5, so output also will rise by 5. Input further rises by 5, capacitor voltage is constant, then output also further rises by, output is also rising by 5. I hope you get it. I need to write a proper shape. Further, input after reaching this, when input reaches 8 volts, by that time output reaches only 0 volts. Output is completely negative. Output is negative means voltage across the diode is negative. Diode cannot conduct. Hence, the capacitor can neither charge nor discharge. Further, input is rising by 5, output also, sorry, input is falling by 5, output also falls by 5. It continues. Are you not getting the same shape as that of the previous one? Whatever the shape you have here, the same shape you can see even here also. The only difference is the capacitor voltage. Here, the capacitor has charged up to the peak amplitude. The capacitor charges up to the peak amplitude. In this example, the peak amplitude is 5. And in the second example, the peak amplitude is 8. The capacitor charges up to the peak amplitude, but the output equation does not change. In steady state, the output waveform is this way only. Please do remember this. It's a very, very interesting point. Okay. Next. One more case I'm taking. It's a standard output. That's it. Okay. I'm taking a clamper in which the output is, my input is -1 plus 5 sin omega t. -1 or -2, anything we can take. Then what about the output? Again, if you take the waveforms, it is something like -1 volt. V input is equal to -1 plus 5 sin omega t. Then what about V capacitor and V output? Here, from this point to this point, input is negative. Input is negative means diode does not conduct and the capacitor cannot charge. Let me take this interval, this instant as T1 and this instant as T2. From up to 0 to T1, diode does not conduct. Even though you have input, input is negative, diode does not conduct. So 0 less than T less than T1, diode does not conduct. Okay, and acts as open circuit. And V capacitor is equal to 0. Capacitor acts as short circuit. The capacitor can neither charge nor discharge. So here V capacitor is 0. Then what about V output? V output is equal to V input. Capacitor V capacitor is 0. So if we know V input is equal to V capacitor plus Vd implies okay implies we can write Vd, V capacitor is 0, Vd is equal to V input. Means whatever the negative value of input you have, that can be seen at the output. Next, T1 to T2, input is positive. As input is positive, diode starts conducting. T1 less than T less than T2. During that time, what happens? Diode conducts. And capacitor starts charging towards V input with time constant RF into C, or tau C is equal to RF into C. Means the equivalent circuit is like this. There is a current flow, input RF, and the capacitor will charge like this, and VD or V output. So to what level the capacitor will charge? At T is equal to T2, V input is reaching its peak amplitude. How much? It is 4 volts. And this negative peak is minus 6 volts. At T is equal to T2, capacitor charges up to the peak amplitude of 4 volts. Or I can write at T is equal to T2, V input is equal to 4 volts, the peak amplitude. And due to small delay, and due to small delay, V capacitor is not exactly equal to 4. It may be slightly less than 4, 3.9 volt. Like this, for our understanding purpose only, I am writing it. So, somewhere slightly less than that. So, for T greater than T by T2, V input is falling below its peak amplitude, and by that time, the capacitor voltage reaches 4 volts. So that Vd is equal to V input minus V capacitor. It is 3.9 minus 4 is equal to minus 0.1 volt. Diode is experiencing negative voltage from anode to cathode. Immediately the diode becomes off. Once the diode is off, there is no path for the capacitor to neither to charge nor to discharge. Okay. So, what is the voltage across the capacitor now? It is 4 volts, which is the peak amplitude of the input. Every time the capacitor will charge up to the peak amplitude of the input. That's it. Okay. So, this is the idea. Then what about VD? VD is equal to, or V output is equal to V input minus V capacitor. What is V input, friends? V input is minus 1 plus 5 sin omega t, and V capacitor is 4. Ultimately, your answer is minus 5 plus 5 sin omega t. Same as the answer of previous two cases. Means, again here you can see, and here the capacitor is charging up to 4 volt peak amplitude. Later T2, T is equal to T2, diode is off and the capacitor can neither charge nor discharge. From here onwards, the input is falling by, right here, from here to here, the input is falling by 5. Okay, here it is, during this point, it is 0 only. Capacitor is charging, it is almost equal to your input. And here to here, input is falling by 5, the same fall you can see at the output. Next, from here to here, input is falling by another 5. That another 5 volts fall you can see here. Again, from here to here, okay, the input is rising by another 5. It will also rise by another 5. Again, from here to here, input rises by another 5. It will rise by 5. So ultimately, your output wave shape is, right, something like this. Always your VD is negative. Is it not so? Our VD is negative. Anyway, don't worry about the waveforms. Just look at the concept. Waveforms, right? I wrote some here and there. Doesn't matter. And this particular portion, I can say this is the transient. Okay, this is the idea here. This is how we can see the analysis. All these three cases. So input may be like 5 sin omega t, or something like right, three cases I took, no, 3 plus 5 sin omega t or minus 1 plus 5 sin omega t. If you take all this, in all these cases our response is same. Okay. Again, there is in all these cases the capacitor voltage is changing. The capacitor always charges up to the peak amplitude of the input voltage. Okay. And one more thing is, suppose I have the clamper, same clamper I am taking. It is like minus 6 plus 5 sin omega t I am taking. Then what is the V input peak? Means if you take the output wave, input waveform, how it appears? Minus 6 volts, minus 6 to minus 1, and minus 6 minus 5 minus 1. This is our input I am speaking, not the output. In that case, is there any possibility for the diode to conduct? Never. In this example, the input peak amplitude, V input peak, it is minus 1 volt, which is not sufficient to make the diode to conduct. So, implies the diode never conducts. Once the diode is not conducting, it always acts as open circuit. Means the capacitor never charges. Capacitor always acts as short circuit. So that what is our output, friends? Output is equal to simply input. That's it. So it's not like any input of your choice can be applied. If so, your output will be like this. Input and output are same in this case. Because the input peak amplitude is always negative. As long as diode is not experiencing any positive voltage, diode never conducts. As long as diode is not conducting, the capacitor cannot charge. Capacitor is not charging means with zero initial conditions, it acts as a short circuit and output is equal to input. That's it. Please do remember this. Okay, this is the idea. Next, we have to see if what for the resistor is connected and what is the effect of the reference voltage. Once you understand the negative clamper properly, just like that, you can analyze the positive clamper. Of course, I explained only with sine wave. If it is a square wave, what is the response? We just have to see.